Hello, this is Mr. White, and in this video we are going to determine the domain of a function algebraically. Notice I've crossed out range. That can be done algebraically, but it's a bit trickier, and so we're going to just focus on domain here. Alright, in the last video where we determined domain and range graphically, this was the function that we used. And I want to go ahead and tackle that same function algebraically and show that it agrees with what we determined graphically. So I'm going to move the image of the function off to the side and say let's just focus on the algebraic model here. So I got the graphical model out of the way, and let's focus on the algebraic. And I'm going to say there are two things that typically restrict the domain. You know, for a lot of functions, x can be anything. X can be any real number, but there are two things that usually restrict the domain and say, no, it can't be that number or that set of numbers. And one thing that restricts the domain is anything that causes 0 in the denominator. That's one thing you need to be on the lookout for, denominator. We cannot let the denominator to be 0. You know that you can't divide a number by 0. So essentially we're going to pretty much ignore the numerator here. And we're going to just focus on the denominator and ask ourselves, what is going to make that equal to 0? So I'm going to write this. I'm going to say that denominator, x squared minus 4x plus 3, we cannot allow it to be 0. Okay? Thankfully, that is a fairly easy quadratic to factor. So let's go ahead and write that inequality as x minus 3, x minus 1 cannot equal to 0. It works just the same way as solving equations. The fact that this is an inequality doesn't really change our process. This tells us that x cannot equal 3 and x cannot equal 1. Again, we're used to having equal signs here, but we're just changing them all to not equals. So what I suggest you do is conceptualize this as a number line. Think of a number line going from negative infinity all the way to infinity. And picture that x can be any of the numbers along it. Here's 0 in the middle. There are only two exceptions. I have to get rid of the point at 1, and I have to get rid of the point at 3. That's where I'm going to represent that as little open holes there. Okay, so that's the kind of a number line representation. X can be any of the numbers on this number line except for where those two holes occur. So I would say that this stretch of number line, let me use my black pen here, this stretch right here goes from negative infinity, all the numbers from negative infinity, all the way up to, but just stopping short of 1. And I guess I should have labeled my number line up here just to make it clear where those holes are, if it wasn't already. But when all the way from negative infinity up to 1, it does not include 1 because there's a hole there. That's why we put the parenthesis sign. Now this next stretch right here, that goes from 1 to 3, but not including the actual numbers 1 and 3. So we represent that saying 1, comma 3. And I put a U for union in between those two. And the last one, I'm running out of space here, but I think I can do it here, is I'm going to put a U for union. 3 just beyond 3, all the way up to infinity. And as I mentioned in the last video, when you're writing your domain, you should always be going from low to high. So we went from negative infinity up to 1, and then from 1 up to 3, and then from 3 up to infinity. Those numbers should never be decreasing. They should only be increasing. So that is my domain. We did it algebraically, and notice that if you have any notes from the last video, which I hope you do, that is the exact same answer that we got graphically. When we look at the graph from the last video, we see that it is consistent. So hopefully you remember this graph. I know it's kind of cluttered here in the background, but maybe you even still have it on your calculator. So that's a domain. And again, we can technically do range algebraically, but we're going to not do that right now. Okay, so that was case number 1. You want to make sure that you do not have 0 in the denominator. Let's look at the other thing that you'll typically see that restricts the domain. Case number 2 that causes a restricted domain is that we cannot take the square root of negative numbers or negative quantities. Now you may be thinking, what about imaginary numbers, complex numbers that I learned in Algebra 2? You may be happy to hear we're going to just kind of go back to not considering those, to ignoring those. So here, whenever you see a radical, that's a clue that you're going to have a restricted domain, most likely. A couple exceptions to that, but we'll save that for another day. So look at what's underneath the radical. Look at this quantity underneath, and we have to acknowledge that that cannot equal a negative number. We can't let that be negative, because if it was, we would be then trying to take the square root of it. So I want to represent that by saying 3x minus 7 cannot be negative. It has to be greater than, or it can be equal to 0. That's how we honor that restriction. And then again, just like solving equation, we do the same steps. Move the 7 over, add the 7 over to the other side. Divide by 3. And again, I ask you to think of that as a number line. Let's say that right here is 0, and here is the positive number 7/3. And I want only the numbers that are equal to 7/3 or greater than 7/3. So I want all of these numbers. Any number over here is going to give me a negative quantity under the radical. Don't want that. So how do we represent that in interval notation? We say that the domain for this function is from 7/3. Oh, and well, let me just proceed here. I made a mistake here, and I'm wondering if you see it. If you could pause it for a second, see if you note my mistake, because I'm going to go ahead and reveal it here. I said that it can actually equal 7/3. That is allowed, right? So you see what I did wrong here? I need to erase that parentheses and replace it with a bracket. That's how I say it can equal 7/3. That's my domain of this function. I suggest that you go to your calculator just to confirm. Go ahead and graph that on your graphing calculator and confirm that graphically it works. I ask you to do that on your own. Your graph should look something like this, but use the trace button and confirm on your own that that makes sense. Okay, so that was finding the domain algebraically. The two main cases that restrict the domain: anything that makes the denominator 0 of a fraction, or anything that puts a negative quantity underneath the radical. So try this out on your own. Here are 2 problems for you to try. Pause the video, try it on your own. I'm going to reveal the answers in just a second. And I'll also suggest, go ahead and, when you're done doing it algebraically, go ahead and confirm it graphically. And if you choose, see if you can write down the range graphically. Again, I didn't cover doing that algebraically, but just see if you can do the range as well graphically. I do have that to show you here too. So let me go ahead and show the answers. Hopefully you have been a diligent student and done this on your own, and hopefully your answer agrees that the domain on this one is -∞ to -6, -6 to 1, -1 to infinity. Make sure there are parentheses, not brackets, on all those endpoints. And the range, if you did this graphically, you should be getting that. For the second exercise, your domain should be -∞ to 2.5, but with a bracket. And the range should be bracket 0 all the way up to infinity.